In this final video for section 8.6 on power series, we're going to work through example 6, part A and B together. All right, so there's a lot of components that we're going to use from this section in this example. So stick with me, please pause the video, work out any of the computations on your own so that you can be following along. All right, let's get started though with part A. So part A says, find a power series expansion for the function f of x equals arctan of x about a equals 0, and give an interval on which the series converges. Okay, not too bad. So we could think, oh, well, arctan, we haven't seen that function come up in this section. Maybe we have to go back to the techniques of section 8.5 and work out the entire power series. Well, it turns out there's an easier way. So let's go through that. First, let's make some observations. All right, our observations. So let's recall that the arctan of x, if we compute its derivative, so look at the derivative with respect to dx, what is that? What are some things we know about arctan? Well, we know that derivative looks like 1 over 1 plus x squared. Now, 1 over 1 plus x squared looks a lot like 1 minus something, where that something is minus x squared. So I can see that the derivative of tangent of x looks like 1 over 1 minus something. And where have we seen 1 over 1 minus something before? Well, in this section. So that's our first observation, that the derivative of arctan is 1 over 1 minus x squared. But we also know that we have a power series expansion for 1 over 1 minus x given to us a couple pages above. And that looked like 1 plus x squared plus x cubed plus x to the 4th plus etc. And that was for x between 1 and -1. So what we're going to do is use these two observations to help us in this problem. Okay, so how am I going to do that? Well, what I'm going to do is combine these two observations. So we can do that in the next step. So we see that the derivative, and I'll use a different color here, the derivative of arctan of x is equal to 1 over 1 minus x squared. So now I can use this formula for the power series of 1 over 1 minus something to write a power series expansion for the derivative of arctan. So when we do that, what do we get? I'm going to start the next line here. So now we're going to get 1 plus whatever that thing is squared, plus whatever cubed, plus whatever to the 4th, etc. So what I'm going to plug in here is negative x squared, negative x squared, negative x squared, negative x squared. So now if we just calculate this out, we see that the derivative of arctangent is equal to 1. Then we get minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus x to the 10th, etc. So now if our original series was valid for x between -1 and 1, we know that this series is valid for x squared between -1 and 1. So you can convince yourself that that happens, the squared of x is between 1 and -1, if and only if x itself is between 1 and -1. Okay, so now what do we have? Well, now we have the power series expansion for the derivative of the function that we want to find a power series for. So how do we undo a derivative? Well, we need to look at the integral. We need to integrate. So recall the integral of d dx of arctan of x is going to give us back arctan of x. So what we want to do is integrate the right-hand side of, or rather that power series that we just computed in part 1. So let's go ahead and do that. So we see that the arctan of x is equal to the integral of 1 over 1 plus x squared dx, which is equal to the integral of that power series we just computed. And you can check to make sure that that is valid. And the reason why it's valid is because this power series that we just wrote for part 1 is valid and converges from -1 to 1, meaning that we can integrate and differentiate when x is between -1 and 1. All right, so that's equivalent to, so the integral then of this series. So that looks like the integral of 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th, etc. So we can go ahead and take that integral. So I'm going to start with my plus c here, just because I don't want to include it at the end of my infinite terms or my infinite sum. So I'm just going to integrate each term here that I see. So the integral of 1, or the antiderivative of 1 is just x. Antiderivative of -x squared is going to be -x cubed over 3. Antiderivative of x to the 4 is x to the 5th over 5. And again, here's a great time to go ahead and pause the video and check my work. By you actually thinking through these antiderivatives on your own, it's going to be a lot more productive for your understanding of this problem. Okay, so here is what we have got looking like. So just to write this together, we have arctan of x equals the series c plus x minus x cubed over 3 plus x to the 5 over 5 minus x to the 7th over 7 plus x to the 9th over 9th, da, da, da. Okay, so now let's consider what that c is. So notice if we plug in 0 here, well, on the right-hand side, we only get c. So say at x equals 0. On the right-hand side, we only get c. And the left-hand side, what is that? What is arctan of 0? Well, that is just 0. So this tells us right away that the c constant is 0 for us. So now we can just summarize. So part C, let's summarize. Or maybe let's, instead of summarize, we'll write a conclusion. It's better language here. Cool. So what have we just found? Well, we found the arctan of x is equal to this series. So we can write arctan of x is equal to the series x minus x cubed over 3 plus x to the 5 over 5 minus x to the 7th over 7, etc. And we can even write it in sigma notation. So we're going to start with n equals 0 to infinity. And we have this alternating series. So we have -1 that's going to alternate, where our first term is positive. So we'll start with -1 to the n. And then what happens? Well, each of our exponents is odd. So how do we start with some n and get an odd exponent or denominator? Notice then the exponents and denominator match, so that makes it a little bit easy. Well, after some thinking, we can see that if for any given n, if we multiply that n by 2 and then add 1, we're going to get an even, or rather an odd number. We're just going to go through the list of odd numbers. So my series then in summation notation looks like n equals 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1. And so notice where this series is valid. Well, we started with looking at the series 1 over 1 minus something. We determined and where that series was valid from x from 1 to -1 to 1. And then by integrating that series, that doesn't change that interval of convergence at all. The derivative and integral of the original, or the convergence interval of the original function is going to be the same as the interval of convergence when we take the derivative or integral. So then we still have that same interval of convergence. So we can conclude that that is our power series with interval of convergence from -1 to 1. All right, so now let's just go ahead and finish off this example by looking at part B. So in part B, we're asked to use p sub 5 of x. So that's the 5th degree polynomial. So our term on the x needs to go up to 5 or less. Maybe if our power series, has odd or even powers, then we're only going to go up to 4. But regardless, okay, we'll see what that looks like. So use p sub 5 of x from your power series in part A to approximate the value of arctan at 0.5 and compare your approximation with the value of your calculator given for arctan of 0.5. All right, so let's first of all write out that polynomial. So p sub 5 of x is going to look like, so we're just going to take the sum of the first terms up to the 5th degree term. So by degree is just exponent of the x. So here, that would look like for us, x minus x cubed over 3 plus x to the 5th over 5. All right, so that's p sub 5. So now we can evaluate p sub 5 of 0.5. And we get 0.5 minus 0.5 cubed over 3 plus 0.5 to the 5th over 5. So go ahead and check what that is in your calculator. Should be getting something close to 0.4646. So now pick up your calculator again, and I want you to compute arctan of 0.5. What are we getting there? Should be getting 0.4636. So look at our approximation. For the arctan, evaluated at 0.5, and compare that to the actual value. So notice our approximation picks up a good 2 digits of arctan of 0.5. So pretty close. So I hope this gives you some insight about why power series are so important. We can use not even the whole series, but just a finite number of terms in the series to give really good approximations to really special functions that, like trig functions, exponentiating functions like e to a power. And it turns out that how our calculator calculates fancy functions like arctan is not by creating triangles and using ratios and protractors, but is by using power series approximations. So pretty cool. All right, thanks so much for your hard work in this section.